Hello everyone. In this video we're going to be solving a very interesting differential equation. Y double prime equals 2y over x squared, and we're going to be solving for y values. Now what makes this equation pretty interesting is the fact that we have y double prime on the left hand side and we don't have the first derivative. If we had the first derivative in this equation, that would definitely be a separable one, and that would be fairly easy to solve. I think you could call this a Cauchy-Euler differential equation, which obviously kind of tells you what to do. And I'll be presenting two methods. Let's go ahead and start with the first one. So for my first method, I'm going to change the variable. So let's go ahead and set t equals ln x, which means x can be written as e to the power t. Okay? Now since y is a function of x and we were able to write x as a function of t, now y can be expressed as a function of t. Not the same y, but maybe a different y. So let's go ahead and use a different notation like a big Y or uppercase Y of t is equal to small y of x, which means now we're expressing the same function as a function of t. Okay? Now since we know that t is equal to ln x, we can go ahead and differentiate both sides with respect to x, and that would give us dt over dx equals 1 over x. Because t is a function of x, we can differentiate both sides with respect to x. Great. Now, by using the chain rule, we can actually express this in a more interesting form. So now think about the derivative of the small y with respect to x, which is dy over dx. Now we can write this as the d of big Y over dt, because remember, big Y is a function of t, times dt over dx. And as you know, these are not fractions, so on and so forth, but they act like fractions. So when you go ahead and cancel these out, you end up with the dy over dx, but it's kind of like in a different way, because now y, the big Y, is a function of t, the small y is a function of x. Okay? But they are equal, as you can see here. Great. Now, let's go ahead and see how we can proceed with this beautiful equation. Now, instead of writing the d big Y over dt, we can kind of call it something, maybe use a shortcut like big Y of t, or big Y underscore t, or whatever you want to call that, big Y of t, I guess. Now, we can go ahead and write from here, because this is y prime is equal to big Y of t divided by x, because dt over dx is 1 over x, remember? So we can kind of times 1 over x, but I'm going to turn it into big Y of t divided by x. Awesome. Now here's what we're going to do. From here, we're going to compute the second derivative. Why? Because we need that, right? In our equation, original problem, remember, we have the second derivative. So if you differentiate both sides, and of course, in this case, you kind of need to use the product rule. You can think of this as y of t times 1 over x. We need to use the chain rule, right? Or the product rule. Let's go ahead and differentiate both sides. Y double prime is going to be the derivative of the left-hand side, which is the derivative of y prime, or sorry, big Y of t. So I'm going to write it as the derivative of big Y over t over dx, and then times 1 over x, plus the derivative of the second function, which is negative 1 over x squared, times the first function. Okay? Now, so here's what we need to clarify here. What is d big Y of t of dx, right? Let's go ahead and write it down. D of big Y of t over dx can be written as d of big Y of t over dt, because that's a function of t, so we can differentiate with respect to t, and then multiply by dt over dx, again, by the chain rule. Okay? Now let's go ahead and use a quick, like a shortcut notation here, so we don't have to, write these all the time. Let's go ahead and call this big Y of tt. Okay? Great. Now, we do know that dt over dx is equal to 1 over x. Now, we do get a really nice equation from here, which is the d big Y of t over dx equals big Y of tt divided by x. Awesome. Let's see where this takes us. Now, we kind of have 1 over x, okay, multiplied by d big YT over dx is going to give us 1 over x multiplied by big Y tt over x. This will become big Y of tt divided by x squared. Make sense? We basically multiply both sides by 1 over x. But why did we do it? You'll see in a little bit how this is going to help us. Okay? Now, what is the derivative of 1 over x? Obviously, it is negative 1 over x squared. Now, if you take a look at this equation, d of big Y of t over dx equals big Y of tt multiplied by 1 over x, which is this one actually. We can actually from here write the second derivative, which comes from here, because remember, this is what we have right now. And we needed this expression, so y double prime is just going to be y of big Y of tt minus big Y of t divided by x squared. Why? Because it's this expression minus the other expression. Remember that this is going to bring a minus sign. What we did basically is by writing this as something over x squared, we were able to get a common denominator, and now we have y double prime. So here's what we're going to do now. We're going to go ahead and substitute this into our original problem, which is going to give us a constant coefficient differential equation. Okay? Remember the original problem said y double prime is equal to 2y over x squared, and remember the big Y is the same function expressed as a function of t. So now we're going to go ahead and write this as follows. From here, obviously, this is going to give us 2 times big Y over x squared, and we're going to multiply both sides by x squared, and that's going to give us y of tt minus y of t, that's going to be a big Y, by the way, is equal to 2y. And from here we get big Y of tt minus big Y of t minus 2y is equal to 0. And again, this is a constant coefficient equation. Fairly easy to solve. Think about it this way, something like y double prime minus y prime minus 2 equals 0. Or it could be 2y equals 0 in this case, right? So let's go ahead and use the constant coefficient variable or substitution formula. So in this case, the big Y I'm going to replace with e to the power RT, okay? And of course, from here we can evaluate the derivatives. The first derivative with respect to t is going to be r e to the RT, and the second derivative, which is ytt, is going to be r squared e to the power RT, because every time by chain rule, you have to differentiate RT with respect to t. Now, when you substitute this into the equation, you're going to get something like this. R squared e to the RT minus r e to the RT minus 2 e to the RT equals 0. Remember, we had minus 2y at the end. And obviously, we can pull out e to the RT. That gives us r squared minus r minus 2 equals 0. Since this cannot be 0, this has to be 0. Okay? And how do you factor that? It's factorable, right? It's r minus 2 multiplied by r minus 1 equals 0. And from here, you get r equals 2 and r equals negative 1, which gives us the solutions e to the power 2t and e to the power negative 1t. So we can go ahead and put those together to get big Y of t as a function of t, c1 e to the power 2t. Remember, we take the linear combination of these two independent solutions, linearly independent solutions, obviously, and we kind of put those two together. So that gives you the big Y of t. Now let's go back and return to the variable x. We now know that t is equal to ln x, and obviously e to the power 2t is just going to be e to the power 2 ln x. But remember, you can write it as e to the power ln x to the power 2, which is x squared. You could also arrive at the same result by putting the 2 here by using properties of logarithms. It's just x squared. And then the other one, e to the power negative t, is just going to be e to the power negative ln x, and that is e to the power ln x to the power negative 1, which is x to the power negative 1, or just 1 over x. Beautiful, right? So from here, we do get two beautiful solutions. So how do you put it together? Well, the y of x at the end is just going to be made up of these two. c1, this becomes x squared, and c2 becomes 1 over x. Obviously, you can also write this as c1 x squared plus c2 divided by x. So that would be the solution for y, and again, y is a function of x at the end. This is basically the general solution, and what is crucial here is recognizing that when you differentiate the big Y of t with respect to x, you must use the chain rule, because big Y of t, which is this one I'm talking about, depends on t, it doesn't depend directly on x. That's why we get that big Y t over x in our equation. Okay, so far so good. Hang in there, because we're about to do the second method, and let me know which one you like better. Okay, great. So now we have this Cauchy-Euler equation again. Y double prime is equal to 2y divided by x squared. And from here, we can kind of cross multiply. X squared y double prime is equal to 2y. Now let's go ahead and put everything on the same side, which will make this equation look much, much better. Now, you can safely say that this is really a Cauchy-Euler equation, because as you can see, the power of x agrees with the power of, or the order of the derivative, right? Now, and again, you might be saying, why don't we have an x in the equation? We don't have the first derivative. So x squared would go with the second derivative, x would pair up with the first derivative, and x to the power 0, which is 1, would pair up with the y. That's what we have here. Great. Now, in these kinds of scenarios, there's a very nice, actually a much, much better way to do it, which is why this is the second solution or second method. You can replace y with x to the power m. Now let's go ahead and see what happens when we do that. Because of the agreement between the order of the derivative and the power of the x, you're going to get y prime as m x to the power m minus 1. And of course, if you do the second derivative, you're going to get m times m minus 1 times x to the power m minus 2. You kind of get like a descending powers or consecutive numbers as coefficients. And then when you plug everything in, you're going to get x squared multiplied by m times m minus 1 times x to the power m minus 2 minus 2x to the power m equals 0. And obviously these two will multiply and give you x to the power m. So you can kind of pull that out. And inside you're going to have m times m minus 1 minus 2 equals 0. And guess what? This is not going to be 0. Therefore, this needs to be 0, which is m squared minus m minus 2 equals 0. Does that look familiar? It should. Now, this is factorable again with the same method, m minus 2, m plus 1 equals 0. From here, m equals 2 and m equals negative 1 are the solutions to the quadratic. And of course, we assume that y could be written as x to the power m, but there are two possible values. So now we can do the linear combination of those two solutions, and that'll give us c1 x to the power 2 plus c1 x to the power negative 1. Actually, sorry, that's c2 times 1 over x, which is c2 over x. And again, this gives us the exact same solution, but I think this method is a little bit shorter, don't you think? And obviously, you don't want x to be 0 in this case, do you? And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time in another video. Until then, be safe, take care, and don't forget to check out aplusbi as well. And until next time, bye-bye.